So we've talked about rotation, and I would like to talk about what causes rotation. Well, what causes linear motion? Forces, right? Forces results in accelerations, and that's describing the motion of an object. Um, so to get something rotating, we must have to apply a force to it. But the story is a little more complicated than that. So imagine you're going to push a door, right? So what does a door look like? Perfect. But let's say you're approaching, I don't know, the outside of a store, and it has a bar for you to push right here, right? Where do you push to open that door? Well, it depends on where the hinge is, right? If you look at this picture from above, so here's the door from above. We could imagine applying this force in a couple different places, right? We could apply the force here. We could apply the force here. We could apply a force here. We could apply some ridiculous forces like here. But and that's all the same size of force, right? Or that's at least my intention, is for those all to have the same size. Those are all a force. But the resulting rotation of the door will be different for each one of these. So let's say I know that the axis of rotation, the hinge, is right here. So this is the axis of rotation for this door. And now I can say, well, even though they're all the same force, let's label these as 1, 2, 3, and 4. Even though these are all the same force, the effectiveness of these, you can say 1, not effective. Right? If I push at the hinge, I am not going to rotate the door, and I'm going to hit my head against the door and look like an idiot. And that's okay. It happens. If I push at 2, I can call that somewhat effective. If I push at 3, this is maximally effective. So it looks like if I want to cause rotation, I need my force to be applied far from that axis of rotation, right? And I could see, like, here's an R. It's like R2. There's an R3 here. But I can also get force 4 there. Force 4 is applied at R3, right? So it's applied at the right place, but the angle is wrong. The direction is wrong. If I'm pulling against the axis of rotation, that's not effective. So if I want to capture this in an equation, right, I would say, let's see, clearly this depends on force. This, what do I mean this? I mean trying to capture the effectiveness of a force in causing rotation. So the magnitude of the force matters, right? I could make the rotation due to 2 match the effectiveness of the rotation due to 3 if I push twice as hard. All right? So the magnitude of the force matters. Where the force applies, it matters. Sometimes we say R times F. And the angle also matters. And this is the angle between, if I measure the angle between, let's use a different color. The angle between R and F. All right, so like there's an angle, and the angle between these two is 180 degrees. So I need, when the angle is 180 or 0, I need this to give me the smallest possible value. And when the angle is 90 degrees, I want it to give me the maximal value, right? That's a sine. So this captures all of the bits there. We define this as torque. So let me move that so I can put that in there. This is torque. We use the Greek letter tau. Okay, the units for torque here, it must be a Newton times a meter, which, if you recall, a Newton meter is a joule. That's a unit of energy. But giving a torque a unit that is the same as energy, it's kind of happenstance that happens, but a torque really isn't energy. So even though the units are the same, we leave the units for torque as a Newton meter. Okay. Okay, great. So a torque is it's a rotational force, but again, it's not exactly a force because it is a force times a distance. So it's a torque. Okay. How does that modify Newton's second law? Well, let's think about that. Newton's second law is F equals ma. But if we're talking about Newton's second law for rotation, I really want to think about how does a torque cause angular acceleration for some object? How does a torque cause angular acceleration for some object? Okay, well, mathematically, I could convert this equation into a torque on one side and then acceleration on the other side. But let's draw a picture so that we have an idea of so we have an idea in our head when we're deriving this. So I want a force on something that's going to rotate. Let's imagine rotating a mass on the end of a stick. All right, this is kind of a fabricated example, but there's a reason for that. So let's draw an axis of rotation here. A thin stick and a mass on the end of it. All right, again, that green spot is my axis of rotation. And I'm going to apply some kind of torque to this system. All right, let's say I apply a force. Now, to calculate torque, remember torque is r times F times sine theta. So where I apply this force matters, right? If I apply the force here or here or here, that matters. So remember, a free body diagram models the entire system as a point, but that doesn't work for us anymore because I need to capture where that force is applied as well. So we draw what's called an extended free body diagram, which really just means a picture of just that object. Okay, so let's say we apply this torque. Let's say I know this distance is r. And I want to figure out how can I get from the torque on this mass to the acceleration of this mass, the angular acceleration of this mass, right? So how do I relate tau and alpha, which I expect to be the same direction, right? How do I relate tau and alpha? Okay. Well, I can multiply both sides of this equation by r. So on the left-hand side, I have r times f. And let's assume for now that it's applied in the most effective way it can be applied, so that the sine theta bit is not something I need to consider. I will also recall that, let's write this over here in yellow, that A equals alpha R. Right, so I can plug that in too. So I've got R times F equals M times alpha times R times R. So again, R times F is tau, and alpha is angular acceleration. And what I have left here is mr squared, which is really interesting. Mr squared. So let's define that mr squared as, let's say this. This looks very much like Newton's second law for linear motion, right? F equals ma. But now we have tau equals something alpha. But here's the trick. The proportionality constant between the force applied and the resulting acceleration for linear motion is mass, right? That's an inertia term. Remember, inertia is something's resistance to change in motion. So larger inertia means you have to apply a bigger force to get an acceleration. It's the same thing here, except now our inertia term also depends on how that mass is distributed. Let me explain. Let's say you're trying to rotate a hammer. Right, so how do you draw a hammer? Oh. Sure, that looks like Thor's hammer. Spectacular. So let's say you're trying to rotate a hammer, and you apply some torque to it, and I ask how effective is that torque at rotating the hammer? Well, the answer depends on how you're trying to rotate the hammer. So if I try to rotate this hammer about this axis, and I apply some torque to this, let's apply a fixed torque, I'm going to get a pretty small acceleration out of that, because all of the mass of this hammer is sitting, right here, or almost all of the mass is sitting right here, at a distance r from this, right? What if instead I went to rotate this hammer about, let me see if I can copy that. Great. I want to rotate this hammer about a different axis, right? Let's do like about the head, right? So you grab the head of this hammer and you go to rotate it. Now, the mass of the head is very close to the axis of rotation, right? Some of it is on the axis of rotation. So the torque required to rotate that should be very, very small. So I'm suggesting if I apply the same torque about a different axis, so same torque, I ought to get a much bigger angular acceleration. So this is just an example of it's not just mass that matters for rotation, right? It depends where I'm trying to rotate that mass about, and that's what that r comes in, right? If we're looking up here at the at this term, m times r squared. So when you try to rotate something, its resistance to rotation depends on how massive it is and how far that mass is from the axis of rotation, right? The further that mass is from the axis of rotation, the harder it's going to be to rotate. We capture that in an idea that's labeled the moment of inertia. We use a capital I for this. So for point masses, moment of inertia is mr squared. where again, r is the distance of that mass from the axis of rotation, and m is the mass of the mass. If you have lots of point masses, you would add them all up. So if I had, several, I would say this is the sum. Like say I equals 1 to n, where n is like the total number of m I r I squared. Again, that's just m1 r1 squared plus m2 r2 squared plus dot dot dot. I think you get the picture. Great. But what if I want to rotate like a disc? Right? Like, let's imagine you have a CD, right? You remember what CDs are. So there's a CD, sure. And you click that thing, or like a DVD, it's right, the same sort of idea. You click that thing onto the holder in the middle, and that applies some torque, which causes some angular acceleration for the system, right? And it speeds up to speed, and the laser can read the disc. So if I was going to say, all right, I know the torque and I want to know the resulting alpha, I need to know that moment of inertia. And by the way, this is the first time I've written this equation in this handout, or this video. That is Newton's second law for rotation. Tau equals I alpha, where I is moment of inertia. Okay. So I would need to know, what is the moment of inertia of that solid disk? Well, the disk isn't a point mass anymore. The disk is an extended body. So the moment of inertia for an extended body would be, well, you would have to add up all of the mr squareds for all of the mass on there. But that's a continuous object, so it would have to be an integral of r squared over dm. So let's just say we do that for several objects. So I can actually show you. We have, right? You can integrate that, or you can trust someone else to integrate it. And this is the sort of result you get. Right? So for a thin hoop, here, I'll highlight these as I talk about them. For a thin cylindrical shell, that's just mr squared. There, that's better. All right, because it's all a distance r. All of the mass is a distance r from the center. If it's uniformly distributed, it's half mr squared. Right. If it's uniformly distributed, it's half mr squared. If you have a solid sphere, it's 2/5 mr squared. If it's a thin spherical shell, right? So like a tennis ball, right? So the solid sphere would be like a bowling ball. The thin spherical shell would be like a tennis ball, where more of the mass is at the edge. If you have a long, thin rod, this is another like common situation. It depends on how you're rotating it. If you're rotating about an end, it's 1/3. If you're rotating about the center, it's 1/12 ml squared. And again, those are exactly the same object, right? A long, thin rod with a mass m and a length l. If you're rotating about the end, like a baseball bat, right? That's not uniform, but I think you get the idea. A baseball bat is intended to be rotated about one end, so more of the mass is further away. So it should be larger than, say, how you rotate a baton. Or a baton, typically you rotate about the center, so the furthest that any mass is away from the axis of rotation is L halves. And so 1/12 here is smaller than 1/3. That's why that's lower. So we have these situations, and there are also equations for other common situations, like say a solid rectangle rotated about an axis through its center one direction or the other direction. Has a specific equation. But again, once you derive those once, you don't have to derive them again. Right? You can just look at the table of what has been derived. So to conclude, Newton's second law. Oh, let me go here. So to conclude, torque is a measure of how effective a force is in causing rotation. It depends on how big the force is, where the force is applied relative to an axis of rotation, and the angle between that force and that distance between the where the force is applied and the axis of rotation. So torque depends on what you're calling the axis of rotation. Often in a problem, an axis of rotation is clear where that is, but not always. The resulting acceleration depends on the moment of inertia of that system, and the moment of inertia also depends on where the axis of rotation is. So this equation is actually an infinite number of equations, because you can change the axis of rotation. Again, if your object is literally rotating, there is an obvious place to call the axis of rotation, right, wherever it's rotating about. But if it's not, there's some gray area. And again, moment of inertia for point masses is mr squared, or you can call it the sum of mr squared if you have lots of objects, lots of point masses, or there's an equation for this for extended bodies. And we'll see examples for all of these in the coming videos.